Good afternoon. In this lecture, I will talk on diffusion through a porous material, and the last lecture I was just talking about the bulk diffusion and Knudsen diffusion. So, two type of diffusion that may be dominating in the catalyst pore, that is, one is the bulk diffusion, which is because of the pore size and the mean free path. So, this is the mean free path, which is from the kinetic theory of the gas, that is the distance travelled by a molecule between two consecutive collision, and pore diameter, if I write it size, average pore size. So, that is something which we are talking here, this one, the radius or the size of this diameter of the pore. So, when the molecule diffuse inside or molecule move must transport through that, and they collide among themselves, and simultaneously they collide with the pore wall also. So, if this mean free path of the molecule is much more greater than the pore diameter. So, that will happen when the pores are wider, right, the larger pore. So, that time the mean free path of the molecule is larger than the, that is much higher. So, what will happen? The molecule will collide among themselves, right. So, just let me say that in the different way. I am just going to change it, that lambda, which is the mean free path of the molecule between two consecutive collisions, right. And if this between two consecutive collisions, if the molecules travel a distance, right, lambda, which is less than the pore dia. So, in one way, just basically the simplicity I would like to say that this, if d is pore diameter is wider, right, larger than the mean free path, right, then it is a bulk diffusion, right. So, just to clarify it, that when the d mean free path of the molecule, right, that is the distance travelled by the molecule is more compared to the pore diameter, the collision between the molecule will be more, right. In that case, so that time the mean free path is less, right, distance travelled by the molecule between two consecutive collision is less, right. So, that time your bulk diffusion is dominating. So, it means when lambda is less than the pore diameter, then the bulk diffusion will take place, right. So, that will happen when the pores are wider, right, in a bigger pore. When the pores are smaller, that is something, the second case, if the pores are smaller, then the mean free path. So, mean free path is wider, that is when the molecules are colliding, the distance travelled between two consecutive collision is large, right, compared to the pore diameter. So, what will happen in a small pore? So, that time the collision with the wall will be more, right, and that is your Knudsen diffusion. So, just to distinguish again what I am saying, in a small pore you will have the Knudsen diffusion, right, and in larger pore you will have the bulk diffusion, right, and that is related to when I say that mean free path. So, mean free path is smaller, right. So, compared to the pore diameter. So, it means that is lambda is less than the pore diameter. So, you will have a bulk diffusion, and this case is your Knudsen diffusion. Okay. So, these two kind of diffusion are very dominant in the catalyst pore, and that will be function of temperature and pressure, right. Whereas, Knudsen diffusion is dominating based on, as I defined earlier also, 9.7 into 10 to the power 3 r bar, which is the mean pore radius, under root of T divided by m, where T is the temperature in Kelvin unit, right, which is mentioned here also, this one. So, T is temperature in Kelvin, m is the molecular weight or average molecular weight of the gas, and r bar is the pore radius in centimeter here. So, dk will be in the unit of centimeter square per second, right. So, Knudsen diffusion is dependent on temperature by square root, right, whereas this, if you look at here, this diffusion, bulk diffusion, that will be a function of temperature as well as pressure also, right. So, temperature, it is to the power 1.75, right, T to the power 1.75. So, there are different correlations for this bulk diffusion calculation and Chapman and Scott correlation, because it depends on the root mean square velocity VRMS as well as the lambda mean free path of the gas molecule, right. So, that is from your transport phenomena, and when you have these two, that is dk and dB, bulk diffusion and Knudsen diffusion, then you can calculate the combined diffusivity dC, that is known as combined diffusivity. Right. So, combined diffusivity is defined based on 1 by dC is equal to 1 by dB plus 1 by dK. Right. So, this is how we define a combined diffusivity, which is a contribution of the bulk diffusion coefficient and the Knudsen diffusion coefficient. Now, this is just a straight pore when we define a pore which is just single cylindrical, right, straight cylinder pore. But in general you will see that pores are not straight cylindrical, they may be in zigzag path like this, right. It may be interconnected also, right, like in zeolite cage channels, they may have channel. So, we need to look at these parts, that is the path may be tortuous also, it is not in a straight cylindrical, you have the defined length, right. So, we define again a term which is known as effective diffusivity. So, now we have bulk diffusion coefficient, Knudsen diffusion coefficient and combined diffusion coefficient, and now besides that another term which is known as effective diffusivity in pore. So, whether you say effective diffusion coefficient or diffusivity. Now, this is a contribution of the porosity, because I told porosity may be different epsilon p, right. It is depending whether pores are straight cylindrical, right, path which is travelled. So, that is known as tortuosity, right. The pores are not straight cylindrical and they may travel a zigzag path, right. So, a parameter or a term is required which is known as tortuosity. And what is tortuosity? The definition says actual distance travelled between 2 points divided by the shortest distance between 2 points, right. So, actual distance travelled, just as an example, if pores are straight and cylindrical like this, then the distance travelled actual and straight, that is same, right, that is this, and shortest is also the same, right. But if the pore is suppose just for example in this shape, right, then what is the actual distance travelled? Suppose this is both dimensions are in L, right, average dimension, this side is L, this side is L, right, just like a right angle here. So, actual distance travelled by a molecule will be this, right, up to this end, suppose like this, and shortest distance will be this between 2 points, right. So, shortest distance is L square root of 2, actual distance is 2 L, right. So, 2 L is the actual distance travelled divided by the shortest distance, that is L square root of 2. So, in that case the tortuosity will be just square root of 2, right, just as an example. But when you see a pore, the pore will be like this. So, one has to calculate, and the tortuosity in a pore can be measured, it is not difficult to measure, one can measure just by doing the adsorption experiments, right, using nitrogen gas and pass through that catalyst bed, and then one can measure it, right. So, one can design a setup to look at the tortuosity of a catalyst. So, once tortuosity is known, porosity is already calculated, porosity definition all of you know, pore volume divided by the total volume, right, that is the volume of the pore in a catalyst divided by the volume of the solid material plus volume of the voids, right. So, this is your porosity. Another term which is defined is known as constriction factor, right. Constriction factor, that is related to your what I discussed here, sigma c, which is a function of beta. So, sigma c is a kind of constriction factor which is defined based on the beta. What is beta? Beta is defined whatever I have discussed here, which is given here and defined here also. So, that is a function of this area and this area, right, that is the ratio of largest area divided by the smallest area. So, that is known as beta. So, your constriction factor sigma is function of beta, where this is suppose your A2, this is your A1. So, beta is A2 upon A1, right. So, it is defined here that beta, suppose sigma beta is 1, then sigma is 1, right. This is a straight cylindrical pore, just like that, right. The largest area and smallest area both are same, right. And in rest of the case, suppose beta is 10, then sigma is 0.5, right. If so, typical value which generally used for the catalyst, most of the time we take 1 if nothing is defined, otherwise sigma is 0.8, tortuosity roughly between 3 to 6, right. So, these values are generally taken, porosity roughly 0.35 or 0.4, right. So, actual values has to be determined experimentally, but if information is not available, then the porosity between 0.35 and 0.45, this is the typical value of a porous material, right. And same thing for the constriction factor, sigma is generally taken 1, right. So, sigma basically is nothing but the variation in the cross sectional area, which is normal to the diffusion and is a function of ratio of maximum to minimum pore area, right, that is. So, effective diffusivity takes care your now porosity, right. So, porosity when I say, that is the pore volume divided by the total volume, right. Tortuosity, which are the pores which are not straight cylindrical, that can be considered by considering this value of tortuosity, and the diameter of the pore may not be uniform throughout. So, you have defined a term which is known as constriction factor and then finally, effective diffusivity, right. So, effective diffusivity is defined as now combined diffusivity times the porosity, right, times the constriction factor and divide by the tortuosity, right. Sometimes most of the time you will see that this sigma c is taken as unity. So, most of the time we define the effective diffusivity d E is equal to epsilon p, that is porosity, times whatever the second term which is your combined diffusivity divided by the tortuosity, right. So, that is the definition of effective diffusivity. So, whenever we write a diffusion equation into a pore of a catalyst, this term will be used instead of this, right. So, if this is non porous material, then you can say that diffusion has as such this has no meaning, and then it can be just your the combined diffusivity if that contributes in the pellet. So, once this is known, combined diffusivity, one can write down the diffusion equation, right. So, this is the diffusion or a formation of a differential equation, rather just I will go in the simplified form of the differential equation in a spherical geometry. But before going to a spherical pellet, catalyst pellet, one should know what happens in a pore which is straight cylindrical. Diffusion in a straight cylindrical pore, right. So, you know that something, if I write a radius of the pore r, some average radius, I am talking a single pore, right, and through which the gas species is diffusing, right. So, when I say the diffusion, it means you are presuming that the mass transfer contribution which is from the external surface, right, or the something which I say that when it reaches to the mouth of the pore, here the concentration is known to you, right. So, this is some kind of boundary condition, and this is your z is equal to, suppose I say 0, and this is z is equal to L, length of the pore. So, between these two, how the points, how the concentration change, that will depend on the pore diameter, right. A small pore or large pore, what I said, small or larger pore. So, there will be a kind of concentration profile in the pore, right, and from the understanding of diffusion, you know that diffusion takes place because of the concentration gradient, right. So, it means a concentration profile will be there, and how to find out that concentration profile in one, because if I am saying that it has reached to the pore mouth and here the concentration is something like CAS, concentration at the surface of the reactant species. So, let us consider a single first order reaction. So, I am just before going for the pellet, just giving you some idea that how to write a differential equation in a catalyst pore which is straight and cylindrical. So, single pore, right. So, what is the equation? You know that now this is something given by the fixed law of diffusion, because it is governed by the diffusion. So, fixed law of diffusion now will be written d E times d C A, concentration of A, as a function of z, right. So, I am assuming that there is no diffusion in the radial direction, everything is diffusing into the axial direction, which is your direction z or whatever the convenient dimension one can select, right. So, this is your flux, right, multiplied by the area normal to the diffusion. So, pores are this straight cylindrical. So, area of this cross section which is pi r square, right, simple. So, the equation is simply input minus output, as usual you have written in minus out minus disappearance because of chemical reaction. So, minus R A, which is based on your choice is yours. So, surface reaction suppose, right. So, in a differential section of that pore you can write a balance here, right, or one can write the complete pore, but since you are writing that concentration profile. So, it is changing because diffusion and chemical reaction. If there is no chemical reaction, there this term will not be there, right. So, minus R A, suppose if I define it based on per unit surface area, choice is yours, right. So, now if you define it based on per unit surface area and this dimension is a delta z. So, surface area of this differential section, right. This is something like that input here. If you have taken a differential section, you cut it and the reaction will take place on the surface of the solid, right, this. So, that will be R A into 2 pi r delta z, right. Basically, the area of this solid surface section, right, on which the reaction is taking place on this surface, right. So, circumference multiplied by the thickness of that. So, this is your surface and disappearance what I say, and that is 0 because you are writing a steady state. So, standard differential equation or mass balance equation remains same, that is input minus output minus disappearance because of chemical reaction is equal to 0. So, if you write it now, so what you will get simply pi r square pore radius times minus d E d c by d z of A in, this is in at z, minus same thing, that is pi r square times minus d d c by d z at z plus delta z, right, in minus out minus disappearance. So, let us assume a first order. So, k times C A, right, concentration which will change down the length of the pore, right, k times C A. So, this is based on surface reaction. So, I will write it subscripted as S, K S. See, one can write based on volume. If it is volume, then it will be pi r square delta z, right, area of cross section into difference z and delta z, right. If I write based on surface area, so it is 2 pi r delta z. So, times 2 pi r delta z is equal to 0, right. So, everything is, if you look at this r is the radius of the pore, so constant. So, one can very easily divide this equation, right, and take the limit delta z tends to 0 as usual for the formation of the differential equation. So, this equation which is now you can cancel because this is a constant here, it is not in radial direction, otherwise this will not be cancelled, but this case it can be cancelled because r is the radius of the pore and there is no flux, no change in that direction. So, basically what is the equation you have is, if I just cancel it this or divide it by pi r square. So, I have minus d E d c by d z at z minus the same thing at z plus delta z minus this will be 2 r k s, right, times this delta z is equal to 0, right. So, I can divide by delta z and take the limit, that then it will become minus d E d c a by d z minus this is at z, the same thing evaluated at z plus delta z divide by delta z, right. And the second term is your 2 times k s C A divide by small r, right. So, what left here z and z plus delta z, right. So, ultimately the equation has come in the form of simply you check it d 2 C A by d z square, right, minus 2 k s C A upon r is equal to 0, right. F at x plus delta x minus f at x, right, this is minus d dca by dz. So, this minus this, that is your d2ca by dz square minus 2 ks upon ca r is equal to 0. This is a diffusion equation in a straight cylindrical pore having radius r, right. So, now if you want to check the concentration profile in a pore of a catalyst, you can very easily solve this equation, and let me check the relationship between Ks surface reaction rate constant and volumetric, because you should know that also. See, how do you define rate, right? That is either based on per unit surface area of the catalyst or per unit volume of the catalyst or per unit mass of a catalyst, right. Suppose if I have written here in terms of per unit surface area, this means this is the moles reacted per unit, that is moles reacted per unit time per unit surface area of the catalyst. So, what is the surface area here? The catalyst is 2 pi r L, right, just for one pore I am talking, right. So, this is basically n times 2 pi r L, which is your BET surface area in one way, right, when you define it per unit mass. So, this is now total moles which have been reacted, right, that is moles reacted per unit time per gram catalyst into the per unit surface area. So, multiplied with surface area to moles reacted, and if you can correlate it based on R A triple dash, which is based on volume, right. So, per unit volume of the catalyst. So, what will be here unit? Pi r square L for one pore if I just do, right. So, what is the relationship between these two? Is equal, so R A S is equal to, simply if you check here, R A triple dash into small r divided by 2, right, the other terms gets cancelled, right. And if I say that this is a first order rate, so this is k times CAS based on surface concentration, and that is also the same thing. So, this is Ks basically, I will write it a double prime, right, because this mass rate, this is rate constant based on surface area, and this side it is based on K triple dash, right, into R divided by 2 times CAS. So, what is the relationship between rate constant based on surface area and volume? I can write that K triple dash is equal to 2 times K, which is based on surface area, either you write double dash or you write K subscripted as S divided by R, right. So, in that case, what is your equation now, which is earlier this one. So, I can write this in this form also, d2Ca by dz square minus 2 Ks upon R can be written based on K triple dash or V, rate constant based on volume unit now, times Ca is equal to 0. So, this is the kind of differential equation which you must have read many times, right, and solution of this equation, differential equation is known, right. Either you write in the form of hyperbolic function, right, A1 cos hyperbolic say mz, if I just say define some phi. Sometimes what we do, oh, I missed one term here which is dE. So, that dE is always here, right. So, this becomes here. So, d will be, if you add d, so that is d times this. So, I will write it k by d, right. So, diffusion coefficient is always there throughout. So, now this kind of equation can be solved, right, and this if you remember or if you just see, phi is defined Thiele modulus, which is here k by d for the this case, right, and L is again here. So, L under root k by d I will write here. So, that is again one term here, length of the pore, which is missed here. So, that is 2 pi r L. So, delta z which is written here. So, that is fine, right. So, 2 pi r L which comes here. So, here it is, this L will be 2 pi r L into pi r square L. So, that is fine, right. So, that is what phi is defined. Basically, we need a term here which is, this is just I will write not phi, but phi into L I will define basically, just to avoid the confusion, m into L a term which is defined by L under root of k by d here, right, m into L which is now L under root of k by d, right, and this I am talking as phi, Thiele modulus, right. So, the meaning of this, that what if I write the equation in terms of phi, right, I can very easily, this term which is defined L under root k by d is a kind of dimensionless number, right, and this talks for any nth order. If I write L under root of k C s to the power n minus 1 divided by d e, this is for any nth order reaction. I will just come back to this point again, but just to give you the idea here, right. So, this equation which we have defined based on this K s surface area rate constant 2 K s upon r, that has been substituted, and finally, you have the rate which is defined in this case here, which is defined in your original equation or somewhere here. That is what we were defining, K s into C a into 2 pi r z, and finally, you have the definition of phi defined like this, right. So, you have the equation now d 2 C a, if I define it, d 2 C a by d z square minus phi square C a is equal to 0, where phi as I defined, that is basically in terms of the Thiele modulus, right. So, phi which is under root of m by d, that is in terms of this k by d, right, L under root k by d, but defined in this form. So, sometimes we write it m into L also, right, where m is square root of k by d, right. So, if you have this information, so the solution of this kind of differential equation is simply in the form of either hyperbolic function or in the form of C a is equal to, just if I write it, a 1 e to the power m l or phi, right. So, I will write it m z or phi z now, phi z plus a 2 e to the power minus phi z. So, a 1 e to the power phi z plus a 2 e to the power minus phi z, or in the form of hyperbolic function, one can write a cos hyperbolic phi z. So, a cos hyperbolic phi z plus b sin hyperbolic phi z. A kind of differential equation, solution of these you must have read in mathematics course, right. So, what are the boundary conditions to find out A and B, that can be find out. So, what is the boundary condition in this case for straight cylindrical pore? Z is equal to 0, C a is equal to C a s, right, because at the pore mouth the concentration is known to you, and at Z is equal to L, this gradient of concentration, because nothing can diffuse out if the pore is closed from one end, right. So, this is the pore which is closed from the end. So, Z is equal to L, d C a by d Z is equal to 0, right. So, these boundary conditions can be solved, and you can have the concentration in the pore, or you can solve this equation for C a by C a s, right, that is the concentration profile, which will be a function of Thiele modulus, right. So, this phi, which is important property of a catalyst, or just to check whether diffusion is controlling or not, this is known as Thiele modulus, right. And for any first order reaction, phi is defined by L under root of k by d. For any nth order reaction, phi is defined by L under root of k C s C to the power or C a to the power n minus 1 upon d e, like this, right. So, one can say generally high value of phi, because it is related to your size of the pore, right. That is one dimension, characteristic dimension we call. Basically, later on for pellet we talk V p upon S x based on the volume of the particle divided by surface area, but here we are defining it based on the pore, single pore. So, it is length of the pore, right. K is the kinetic rate constant based on volumetric unit, C a is the concentration at the surface, and d is the effective diffusivity. So, most important parameter here is the size of the pellet, right, and the rate constant K, right. So, it means generally if phi is greater than 3 in this case, then we say diffusion is the rate controlling, right, because this value of phi gives you the idea whether diffusion is rate controlling or this kinetics is rate controlling. Generally right now just I have done it, I have not solved the equation. So, basically what is you have to do that Ca by Cs, find out the concentration profile by solving this equation. You can very easily solve this equation, right. So, Ca by Cas, and then you will get a concentration profile, and then you have to find out the effectiveness factor, which I am not covering right now. I will talk little later before I want to go for this spherical pellet. So, first thing that the solution of this equation, which is based on these two boundary conditions. So, one can very easily find out the relationship between Ca by Cas, concentration profile, right, because this is the first equation. Suppose if I use this equation, that z is equal to 0, right, e to the power phi z plus e to the minus phi z, right. So, put your z is equal to 0, Ca is equal to Cs. So, one equation you will get from here, which is simply this is 1, this is 1, the A1 plus A2 is 1, right. And second, z is equal to L dCA by dz is 0. So, this will become differentiation of this, right. So, just first calculate dCA by dz, right. So, that will be phi e to the power phi z, right here, and same thing minus this thing, right, and you have z is equal to L. So, this will come in the form of L. So, solve this equation for Ca by Cs. So, basically it will come in the form of e to the power phi L plus e to the power minus phi L divided by 2, right, if you solve that. So, that is to be done, right. So, I will do that later, but before that, so once you know that these things, so that is for a straight cylindrical pore, how to get the differential equation and get the concentration profile in a pore. So, one thing is clear that when the diffusion resistance is strong, then your concentration will drop faster, right, because depending upon the pore size, that is the characteristic of the pore and the size of the pellet. If you talk a pellet, then there will be a kind of gradient inside the pore. Now, let us look at here the same equation, that is when we look at in this case a spherical pellet now, right. So, the approach is same, just for because that was the simplest case for a straight cylindrical pore, we discussed that. Now, in this case when you look at this is a spherical pellet, right, having some radius, porous material, right. So, a pellet, this is spherical pellet with some radius r and r plus delta r, the material balance will be written, right. A total radius of the pellet is capital R. So, here it was a pore, the right, and here we are talking a now spherical pellet, diffusion through a spherical pellet, and so but equation will remain same. So, this equation which is written here is basically your 4 pi r square, because now in this case basically the diffusion is inward, right, because the gas species will come here and diffuse. So, actually the input is at r plus delta r. If I just take a differential shell having a radius r and r plus delta r in a total spherical pellet. So, basically this is r plus delta r. So, input it as r plus delta r and output is at r, right. But by convention we can just say that the input is still at r, but with negative sign, right, and flux is negative here, and same thing at r plus delta r, right. So, means one can write the differential equation either saying input here minus output here, or one can still say that the flux is in the negative side of that r, right, as r is increasing, right, when r is increasing in this side, but the flux is in the direction of negative r, decreasing r, right, because the concentration highest is here Cas at the surface and then it is decreasing. So, in this case again the equation will remain same, only thing that WAR, which is the flux at any radius r, when I am saying now in here and defined by the same expression of Fick's law of diffusion minus dE dCA by dr, right. But area which is the now spherical cell, right. So, area normal to that plane. So, that will be now 4 pi r square, right, instead of pi r square which was the cross section area in a cylindrical pore. Now, this is 4 pi r square. So, that expression will be WAR into 4 pi r square minus the same thing at r plus delta r, right, and minus disappearance because of chemical reaction. So, there we have defined it based on the area of the pore, right. Here this is the solid mass, solid pellet. So, it is better to define it based on the mass of a catalyst. So, that is the third term which has been written here. The second term which is shown here is R A dash. So, R A dash is the rate of reaction per unit mass of the catalyst. So, mass of the catalyst means it has to be multiplied by the mass of that differential section. So, this is a differential section of the cell having radius r and r plus delta r, right. So, the volume will be 4 by 3 pi r cube at the r into density, right, and the outer section will have 4 by 3 pi r plus delta r whole cube, right, and to density. So, the mass of the differential section will be difference of this, right, or in other words if you solve it, it will become 4 pi r square delta r, that is the volume of that differential cell. So, volume of this differential cell is simply 4 pi r square into delta r, right. That is simply you subtract that 4 by 3 pi r plus delta r whole cube minus 4 by 3 pi r cube, right, and multiplied by the density. So, cell volume is 4 pi r square delta r multiplied by the density. So, this is the basically into 4 pi r square here and then is equal to 0, right. So, that 4 pi r square has been cancelled, 4 pi has been cancelled from this side. So, finally, only the directly the differential equation has been shown here, right. So, if you look at the exact which I have made it separately for understanding that W A r into 4 pi r square evaluated at r minus W A r which is the flux, W A r is minus d d C A by d r 4 pi r square evaluated at r plus delta r minus disappearance unit mass of the catalyst. So, minus R A dash times the density of the catalyst, right, rho c, and multiplied by the volume of the shell, right. And when you divide it by 4 pi r square, right, and take the limit delta r tends to 0. So, your equation now becomes d over dr of W A r into r square minus R A dash into r square rho c is equal to 0, which is the equation shown here, right. So, W A r all of you know is given by Fick's law of diffusion. So, this one is your minus d E d C A by d r, right, and rate of reaction. Now, rate of reaction has been defined per unit mass of the catalyst, but I have now already told you that rate of reaction per unit mass of catalyst multiplied by mass of catalyst will be equal to rate of reaction per unit surface area of the catalyst multiplied by the surface area of the catalyst, which is BET surface area, and that is also equal to rate of reaction per unit volume of the catalyst multiplied by the volume of the catalyst. So, this is what shown here is minus R A dash which is equal to per unit mass of the catalyst can be written in terms of, because this is surface area per unit mass BET surface area, right. When you report BET surface area, you write meter square per gram, right. So, in one way I can write here R A dash into mass of the catalyst is equal to R A double dash into total surface area of the catalyst without any mass unit, right. So, mass has gone here. So, this is your per unit mass data, right, and that multiplied by the rate of reaction per unit surface area. So, either unit can be used as I discussed before also. If you write it based on volume unit, so minus R A triple dash is equal to, because now mass divided by the volume of the pellet, per unit volume of the catalyst pellet. So, that will become density of the catalyst pellet and times the minus R A dash. So, this is the relationship between R A triple dash and R A dash, and if you just now combine these two, you can very easily write R A triple dash which is equal to rho c times S A and times minus R A double dash, right. So, one can very easily write down a relationship among 3, and either in the, when you write either in terms of rate or you define in terms of rate constant, no change, right. So, K triple dash is again equal to K double dash times S A times rho c, right, and here K dash is K double dash times S A. So, one can very easily correlate the K triple dash, K double dash and K dash, right. So, that is what written here, and once you have the idea about that, now this differential equation which is in the flux, right, Fick's law of diffusion, substitute it here in the form of W A r which is shown here, right. So, W A r is minus d E d C A by d r, one can write it in the form of mole fraction also. So, Y A is mole fraction, right. So, C total concentration into mole fraction is your Ca, right, concentration, molar concentration. So, by using this, if you substitute, so your equation comes out to be minus d over dr of minus d dCA by dr times r square minus the same term r a dash rho c into r square is equal to 0, right. So, this is the formulation of differential equation for a spherical pellet. Similarly, one can write the differential equation for a cylindrical pellet also. So, initially I have shown for a pore. In the case of cylindrical pellet, it will be now length of the cylinder, right, and 2 pi r l, that is the approach will be similar what you have seen earlier, right, for a cylindrical pellet when the diffusion is taking place along the length, right. So, here the finally a formulation of differential equation which is d over dr of r square minus d dCA by dr plus r square k dash rho c and Ca to the power n for any, because we have to find out what is R a dash. It can be a first order rate, it can be second order, it can be nth order also, right. So, that is the equation for nth order. So, in simplification if you do, so d2 Ca by dr square plus 2 upon r dCA by dr minus k by dCA is equal to 0 for first order reaction. So, how did you get this? This is just now simplify this equation, right. So, d over dr of r square d dCA by dr, right. So, first function differentiation of second, right, r dCA by dr, and this diffusion coefficient is a constant. So, first thing is that this has been taken to this side, right. So, diffusion coefficient is simply k by, we have just taken divided by d, we are, but you cannot take this r square out, make it clear, right, because this is inside the differentiation equation, right. So, d over dr of r square dCA by dr. So, d over dr of first thing is d2 r square will be out. So, it will become d2 Ca by dr square, right. Second time it will become your differentiation of this, that will be 2 r, right. Now, you can divide by r square, right. So, then it has been divided by r square. So, it will become d2 Ca by dr square plus 2 upon r dCA by dr minus k by d, because this r square cancels now. So, k by d times rho c times Ca is equal to 0, but k by k dash times rho c, I have shown you that k dash times rho c can be written in the form of k triple dash, volumetric rate constant, which can be written based on these three, right. So, the choice is yours, one can write it in form of this same expression k dash times rho c also, right, or you write k dash times rho c, which is written here in terms of this. So, that has been written in terms of volumetric rate constant, just for simplification, because most of the time the rate will be defined per unit mass of the catalyst. So, once this is known, you need a boundary condition, right. So, this is what the equation which has been written here first. So, an equation need to be solved. So, there are numerical methods which are available nowadays, rather one can go with the analytical technique also, very briefly I will talk on that, but it is advisable for this kind of differential equation and to have a concentration profile, right, rather having the final value of the concentration which you get in the analytical approach, it is advisable to go with the numerical techniques, right, and the solutions or methods are available in many software tools, Polymath, MATLAB, as I discussed earlier, right. So, here the important thing what I said is the boundary condition first. So, I think before going this, let us talk on the boundary condition. Right, boundary condition. So, you know a spherical pellet something like this, right, and at the surface the concentration is known, right. If I just say that this is a spherical pellet and this is your concentration. So, there is a film basically if you look at the external mass transfer also, but we have already said that this is not controlling. So, then it can be, if this is CAG and this is not controlling, this will be CAG, known concentration, right, or in general we can write it some known concentration Cs. So, R is equal to capital R, the first boundary condition, R is equal to capital R, your concentration is known. So, Ca is equal to Cs, right, that is the first one, right, and R is equal to 0, that is center of the pellet, Ca cannot be 0, right, that what we will use. One can use dCA by dr is 0, right, because of symmetry also, right, but the important here that R is 0 at the center, the Ca will have some value, it is finite. It cannot be infinite, because down the length the concentration of the reactant species is decreasing, right. So, it means it will decrease with radius inside if you move towards, because diffusion is from outer surface to the inner surface for the reactant species, right. So, this is the first thing, that boundary condition. Second is that why do we need some kind of dimensionless parameters, right. So, we need the dimensionless, because these kind of equations can be solved better and interpreted better for the commercial success, and we need to find out the dimensionless equations, right. So, these are required because it reduces the complexity of the equation, right. The number of variables can be reduced by using this also, right. Simplify operation of calculation and scale up becomes easy, that is the we define some dimensionless parameter and based on that we solve the equation. So, now we have an equation of this form, right. So, this equation d2 Ca by dr square plus 2 upon r dCa by dr minus k by dE times Ca is equal to 0 for spherical pellet, one needs to solve this equation, right. The equation can be solved analytically also, but preference will be given to the numerical technique. So, in this case we are using some dimensionless variables, right. So, define some parameters like psi, right. So, psi is a dimensionless concentration defined as Ca by Cas, right, and lambda is another dimensionless length defined as r by r, right. So, that is any radius r divided by the total radius of the pellet which is known to you, right. So, it means the dimensionless equation psi and lambda. So, this equation can be represented in form of a dimensionless form like this, right. So, now instead of you saying 0.5 mm radius of the pellet or 5 mm radius of the pellet, you can just talk in terms of the position, right, that is r by r 0.2, r by r 0.5, r by r 1 like that, right. So, and now irrespective of the dimension of the pellet, right. So, what means you have a 1 mm pellet or 10 mm pellet, when you look at in a lab scale reactor it is a powder of 100 micron, but when you look at a commercial pellet scale it can be 1 mm or 1.5 mm, right. So, you need not to bother about that. Same thing in terms of the concentration gradient. So, you may start with 10 kilomole per meter cube, right, or you may start with just 1 in terms of the 0.05 gram mole per meter cube, any choice can of the concentration can be used, because we are talking now in terms of Ca by Cas, right. That is what is the concentration at the surface or initial concentration, and now how much is left, right, because rest is reacted. So, that is important here in this case. So, we can use these dimensionless variables, and I hope all of you know this part how to write the equation. So, quickly I have written here in terms of interconversion, right. So, dCa by dr we have to find first, right. So, dCa by dr can be splitted based on chain rule of partial differentiation, right. So, that is simply dCa by d lambda into d lambda by dr. So, that is what dCa is to be written in terms of the psi, and lambda is r is to be written in the form of lambda. So, first thing has been done, that this r has been replaced in the form of lambda. So, dCa by d lambda into d lambda by dr. So, d lambda by dr one can calculate from here, right. So, d lambda by dr is simply 1 by r, and dCa by d lambda now you can split it in the form of psi. So, that becomes d psi by d lambda, right, and times dCa by d psi. So, basically it is dCa by d psi times d psi by d lambda, and dCa by d psi one can calculate from here, right. And if you look at here, so multiplied by the third term which is already there, d lambda by dr, right. So, if you do that, so just for understanding I have written here. So, dCa by dr now becomes your d psi by d lambda, now we have changed it in this form, and differentiation of this dCa by d psi, right, dCa by d psi, that is equal to Cas, right, from this equation, and which is written here, and second term is d lambda by dr, differentiation of this is 1 by r. So, that means dCa by dr has been replaced by d psi by d lambda times Cs by r. Why we are doing this, I will let you know, right, because the reason is that we want to simplify our differential equation for analytical solution, right. Otherwise, one can solve the equation by finite difference method also using the numerical techniques, right. So, similarly one can write d2 Ca by dr square also. So, d2 Ca by dr square is simply equal to d over dr of dCa by dr, you know that, right, and dCa by dr already we have done right here. So, that will simply now d over dr is to be replaced in this form, but you have done earlier. So, overall what you have d psi by d lambda, which is here. So, differentiation of that, because d over d lambda into d lambda by dr, right. So, that is simply d2 psi by d lambda square, which is from here, this differentiation of this with respect to lambda, and again you have d lambda by dr. So, that will be 1 by r. So, that is Cs upon r square, right. Very simple how to change the equation in the that is dimensionless form of the variables. So, that what we have done here. Boundary conditions you know now, because all initially C is equal to C s at r is equal to capital R. Now, it will become psi is equal to 1 at lambda is equal to 1, right. And second, C is finite at r is equal to 0. So, now psi will be finite at lambda is equal to 0, right. So, when you do that, you will have the same terms, right. So, the equation now which is in this form which we have discussed here has been now written like this, right. So, that is what the term, if you look at d2 Ca by dr square, we have substituted dCa by dr we have already defined, right, in terms. So, this will be changed to d psi by d lambda square, that has changed to d psi by d lambda basically here, it is not r, right. So, that is again here in this form, and k by d times Ca. So, that has gotten the term in the form of r square, which we have shown here, all these terms together Cs times r square, which is a constant, right. So, radius of the pellet and surface concentration. So, based on this, the equation has been simplified to this form. So, phi square, which is other than all the term which is psi, and that has been considered as a phi square Thelium modulus, what I defined earlier, right. I will come back again for details of the phi square later, but at this stage this number which has arrived in the writing the equation is simply here k 1 times r square divided by d e, right. So, r under root k by d is your phi, where r is the radius of the spherical pellet, right. And if it is nth order reaction, then this will be written like k for nth order reaction divided by d e times C a to the power n, and that time this phi will be r is r under root of k C s to the power n minus 1 divided by d e, which I had already discussed, right. So, basically for first order reaction phi is r under root k by d, and for any nth order reaction phi is r under root of k C s to the power n minus 1 divided by d e, right. So, we will come back to that point again, because this is very important when you look at a heterogeneous catalytic reaction. The diffusion resistance is very important phenomenon that comes because of the pore size distribution and pore radius, pellet size, right, and one needs to remove them, right. The resistances which is because of the diffusion, that has to be eliminated once you want to study the kinetics of the reaction, right. So, the solution of this kind of equation is possible analytically just by assuming some parameter which relates this y psi and lambda together. Otherwise, it becomes difficult to do analytically, but or one can solve it through Bessel's function, right. So, Bessel's function of different orders one can use here and solve them, right, but the computational methods are better nowadays, and this is one method, one analytical method by which you can solve it, right. So, just if you define a parameter, another parameter which can combine psi and lambda in one equation, right. So, we have defined y is equal to psi into lambda, right. So, it means your d 2 y by d lambda square, right, you can write differentiation of this of that equation which we have already written earlier. So, if you just substitute that, the terms gets cancelled, right, because we are substituting there now d 2 psi by d lambda square and d psi by d lambda, right. So, that second term will get cancelled when you substitute this term, and just for your exercise one can do that, right. Just for understanding one should do that. So, I have written it quickly that if you write y is equal to psi into lambda, then the equation which is written in the original form here in this form, this equation has now been simplified to this form d 2 y by d lambda square minus phi square y, and this equation just I was talking when I was discussing the diffusion in a pore, similar equation here, right. And solution of this kind of equation is very standard, right. That is y is equal to a cos hyperbolic phi lambda plus b sin hyperbolic phi lambda, either you write in this hyperbolic function form or you write it in the form of exponential, right. C 1 e to the power phi lambda plus C 2 e to the power minus phi lambda, right. So, either form, either exponential power or this, both terms can be used here, right. So, in boundary condition I told that at center of the pellet it has to be finite, concentration has to be finite, and at the outer surface, that is the Ca by Cs was 1, right. That is what we have already defined. So, if you use that, A is equal to 0, A has to be 0 rather, this, because at the center of the pellet, that is lambda is equal to 0, your cos hyperbolic phi lambda if you calculate, right. So, cos hyperbolic phi lambda. So, what I will do, y is equal to psi lambda, you have to interpret it like this. So, y is equal to psi lambda, which is a cos hyperbolic phi lambda plus b sin hyperbolic phi lambda. So, your psi is equal to a by lambda times this plus b by lambda times this, right. So, when lambda is 0 you are saying, so this is indeterminate form. So, you need to solve. So, cos hyperbolic phi lambda, because when lambda is 0, cos hyperbolic, this lambda tends to 0 I should say, that cos hyperbolic phi lambda becomes 1, right, and sin hyperbolic term becomes 0, right. So, this says that because lambda is in the denominator, right, also. So, it means your this psi has to be infinite, right, concentration has to be infinite, which is not possible. So, it means your constant A has to be 0. This is the interpretation based on this boundary condition. So, once A is 0, then your simply your y is equal to b sin hyperbolic phi lambda, right. So, psi is equal to 1 upon lambda b sin hyperbolic phi lambda. Use the second, now first boundary condition, that you know that at r is equal to capital R, C is equal to C s, right. So, use that and find out the constant, and you can solve that equation, and that is what written here. So, psi is equal to C A, which is defined as C A by C s, is 1 by lambda sin hyperbolic phi lambda, which is Thiele modulus, divided by sin hyperbolic phi lambda. So, this is basically Thiele modulus here, right. And same expression, because that time I have not shown you, same expression will be used, will come for the pellet also. So, C A by C s is equal to sin hyperbolic phi L there divided by sin hyperbolic phi, right, and that term will be remain there, that is 1 upon L which we are defining. So, I will continue it next time. So, I stop here today. Thank you.